Hello, everyone, and we are live. Can you please confirm in the chat if you can hear me, see me? Is everything clear? I like to make sure that the stream health is fine. So, if you can just tap a yes or type anything in the chat, I'll really appreciate it. So, can you hear me? Yes or no? I want to make sure I see at least several yeses coming in. All right, let's see. Yes. Okay, thank you so much for confirming. Perfect. Okay, awesome. Thank you so much for joining. This is going to be a really jam-packed, informative session on how you can map wildfires with satellite data. And while we're waiting for more people to join in, I'd love for everyone to introduce themselves. So if you can type in the chat your name, organization, country that you're calling in from, and one environmental issue that you're super passionate about. That would be fantastic. And again, if you're comfortable, feel free to add your LinkedIn if you want people to connect. But it'll be great if you can just introduce yourself so people can connect with each other. So while we're waiting for one more minute, please do go ahead and introduce yourselves. Thank you all for the yeses. I really appreciate that. Okay, reading some messages. Let's see. Again, while we're waiting, feel free to introduce yourself. Name, organization, country, and if you want, the issue you're most passionate about solving. This is an opportunity for you to connect with each other because a lot of you are geospatial data scientists joining in from many different countries. So I want to enhance collaboration and efforts if we can through this. So thank you for introducing. Yeah, from Hong Kong. Okay, flooding in this part of the world. Thank you for letting us know. There are fires happening as we speak in Japan, by the way. Christopher from Nigeria, recent graduate of remote sensing. Thank you for joining all the way from Nigeria. Awesome. Oh, we have someone from Brazil, Aline from Brazil, work on emergency management for the mining industry. Welcome. Glad to have you. Okay, so let's get started. We have time, but not too much because we have a lot to go through. Introductions are coming in from Argentina, London, Altadena. Thank you so much for joining. Texas A&M. Okay. All right. Amazing. So with that, we'll get started. This is a session on mapping wildfires and burned areas using satellite data, and we'll be focusing on a very specific case study of Los Angeles. But in the whole process, I want you to take away from this session how you can detect wildfire data, how you can access and download and use it, and how you can map burn severity. So whatever area you are in and calling from, I want to be able to empower you to access the data for your needs in your localities. A little bit about myself. So I'm the executive director of Planet Sapling. We use satellite and sensor data to map climate and biodiversity risks for climate change mitigation, adaptation, and conservation. I'm also the director of operations at Mycelium, which is a local Huntsville, Alabama-based nonprofit focused on accelerating the circular economy through open source solutions. We've created solutions for waste management, food resilience, and we are working on self-sufficient housing. I used to work at a NASA team called Impact, where I worked on modeling and detection of floating marine debris near coastal areas and identifying aircraft contrails using satellite imagery. And my background is in earth science and physics, and I'm working on a graduate master's program in biomimicry at Arizona State University. And so this is just a quick timeline, but essentially I've spent the past over 5 years in geospatial data science. And yeah, my first job was at NASA Impact. Then I joined a climate startup called Climate Engine, where I was for nearly 2.5 years. I developed various risk models for things like extreme heat, wildfires, which you'll learn about, drought, and nature risk. And then just in August last year, I started my company, Planet Sapling. And that's where this effort is happening. And I want to empower communities to use geospatial data for climate action. That's one of the main missions of this company. Okay, so what I'm going to present is the first ever project done by LocalSolve. And LocalSolve is a global network of geospatial data scientists and enthusiasts. You don't have to be a data scientist to join, but the community is focused on creating data projects for climate action. And the mission is to create replicable and open source code and methodologies for local climate action. And what I mean by climate action is mapping things like wildfire damage for future prevention, or mapping flood risk, or mapping extreme heat and potential for green infrastructure. So whatever issue is your community is facing or your locality is facing, we want to create small-scale examples of that, but that's replicable in methodology, and empower you and this community to create that. So with that, I want to credit the team that worked on this along with myself. Magdalena Cortas from Australia, she's a data scientist and AI engineer, helped in creating this application that we're going to feature soon. Palak Agarwal, who's in DC, she is an excellent geospatial data scientist and ML expert. She helped a lot with the vegetation analysis part of this. We have Keenan Eves, who's out in Utah, who is a data scientist and computer vision expert, helped a lot with the burn severity code mapping. We have Emmanuel Alafa, all the way from Africa, who focused on who's a data scientist and geospatial analyst who mapped some infrastructure data for us. We have Kabir Ahmad from Canada, who is a GIS application specialist. He worked on some ArcGIS reporting and is going to work on a ArcGIS story map for this whole project. And then we have Aurélien Collins, all the way from France, who's also a geospatial data scientist, helping with the burn severity code that we have, and water masking, cloud masking. We'll go over all of that. And Vanessa Martin, who's a dear friend of mine in Huntsville, Alabama, also a geospatial data scientist at NASA Sevier, who helped with some NDVI analysis of this project. So I want everyone to get on the same page. So this is just a really quick review of geospatial data, after which I promise we'll get into wildfire mapping. Okay, so there are hundreds of satellites orbiting the Earth, many of which are facing down. That means they're looking at the Earth and monitoring our planet. Geospatial data is information linked to a specific location on Earth. So one of the first layers we have is a base map, and we'll go over what that means. But a base map is pretty much what you see on Google Maps with labels or satellite imagery. And then on top of those base maps, you have things like land cover data, demographic data, wetlands, topography, river data, whatever you want to add. You add layers on top of that base map. But it's really, really essential to have that accurate land cover or base map, on top of which you do more analysis. And when considering satellite data, you want to understand three different types of things: spatial resolution, temporal resolution, and then spectral, which we'll talk about. So spatial is simply the size of each pixel in units of distance. So if we have a 1 meter spatial resolution, that means the pixel that combine and create the whole image, each pixel is 1 meter by 1 meter, or 1 meter square in area. And the lower this number, the higher the resolution, meaning 1 meter is fairly high resolution. But generally a lot of satellite data come in anywhere between 30 meters, 100 meters, 250 meters, or even kilometers. So that means the block or the pixel size is bigger and the resolution is coarser. Now, temporal resolution is the measure of the frequency or repeat cycle. So how often or how frequently does the satellite revisit the same place on the planet? So if the temporal resolution is 3 days, then the satellite comes back to the same place 3 days after. That means you'll get images every 3 days for that region. Now, satellites can also be in constellations, meaning they're paired or in a twin format, like Sentinel-2, A and B. There's MODIS, which is Terra and Aqua. So that can reduce revisit time because they're orbiting the planet in different directions or different trajectories, and that can probably halve the revisit time. I'm not going to click on this, but this is essential, and you'll get the idea. I will send all of these links to you, so you'll have the full presentation at the end. But this is a low Earth orbit visualization. It takes some time to load, and we don't have too much time, but just a quick sneak peek shows you. Let's see if it works. Yeah, this is a simulation of all the satellites orbiting the Earth, and then it shows you in relative near real time where the satellites are orbiting and what locations they're in. So you can even track individual satellites. I will, again, This link is on the presentation. It's a very heavy link, so I'll leave it there. But it visualizes paths of satellites in a 3D model, and you can then detect where each satellite is going and find out the temporal resolution as well. And then raster versus vector. So raster data is continuous, vector is discrete. Raster is image data, like your geotiffs or geotiffs are the most common format, or TIFF files. And vector is more about points, polygons, lines, discrete data that's not continuous. And rasters are made up of pixels, and that's more of the image format that we'll talk about. So again, raster is gridded, vector is points, discrete, raster is continuous. And last but not least, the spectral resolution is the number of bands in a sensor. That means each sensor has specific wavelengths to monitor specific things. And one band is a narrow or wider, but generally a narrow range of wavelengths. Now, the higher the spectral resolution, the more bands the sensor has. And there are two main types of sensors based on their spectral resolution. Multispectral, which is Sentinel-2, Landsat. They have 3 to 10 or 13, just a few, like a couple dozen or less bands. Hyperspectral usually consists of hundreds of bands. That means each band is very narrow. And you can choose from a range of wavelengths to monitor. And hyperspectral is often used for mining, finding out which minerals exist. For example, VIIRS is a hyperspectral satellite. They can also be used for vegetation analysis, something we'll talk about later. Whereas multispectral is more general for vegetation health, like NDVI, or the normalized burn ratio, or the water index, or floating algal index. So you can do many things with multispectral, but hyperspectral, if you want to find out species distinctions or mineral distinctions, you'd use something like hyperspectral data. This is just a quick example of the kinds of bands we normally encounter in multispectral data. So we have a coastal aerosol band, blue, green, red, that makes up the visible RGB imagery. Then you have near infrared, or NIR, and usually you have 2 bands of shortwave infrared, or SWIR bands. And this is just a table. Again, I just included this for your reference when you actually go through these slides on your free time. But this is just an example of spatial resolution, coverage, temporal coverage, resolution, and spectral resolution for various satellites. And I've included a link to NASA Pathfinders for your exploration later on. Okay, that covers the review. If you have any questions on this, you can ask them later, but this was just to get everyone on the same page about some terms that we'll be using. Now let's move on to wildfire detection, what you've been waiting for the whole time. And so what I want to go through in this section is specifically the main categories of wildfire detection satellites, how to use them, how to access them, and when to use which, because it can be confusing. So VIIRS is the Visible Infrared Imaging Radiometer Suite. This provides high resolution fire detection than MODIS. It's widely used for hotspot identification and fire front tracking. I've used VIIRS for mapping fire spread. We will actually demonstrate an application on that. And it's fairly high resolution. It's one of my favorite satellites to use for wildfire detection. Then you have MODIS. MODIS has been working since 2000, provides a really good amount of historical fire records since 2000, and is 1 kilometer in resolution. Has lower spatial resolution than VIIRS, but it still provides historical context. So if I wanted to map historical fire hotspots over the past 10 years, 20 years, I'd be using MODIS. And then we have GOES, which is fairly recent compared to MODIS, but it is the fastest wildfire detection because GOES updates every 5 to 15 minutes. So if you're in an emergency situation and you want to inform fire teams on where is the fire happening, you'll use GOES. You won't use MODIS or VIIRS. VIIRS to some extent, but GOES is every less than 15-minute resolution. So GOES is by far the fastest fire detector we have. Then, so the question is now, how are these fires detected? Do these satellites just see fires and classify it as such, or is there something else going on? So for MODIS, VIIRS, and GOES, one common thing is they use what's called brightness temperature. That means they look at the pixels on the ground and measure the radiance. And using that radiance that's coming out of those anomalies, thermal anomalies, it's calculated into what's called brightness temperature. And when that brightness temperature is significantly higher than the background temperature of the land surface, that's a thermal anomaly. These satellites are not really detecting fires, they're detecting thermal anomalies, or hot spots which are much hotter than the background surface. So what these algorithms do is calculate the brightness temperature difference between, generally speaking, two wavelengths. One is a MWIR, which is infrared 3.7 microns, a short wave infrared kind of band, and then a long wave infrared band, which is 11 microns. And they have these two different infrared bands, which allow you to then determine the BTD, brightness temperature difference, and whichever ones are higher than the background normal land surface temperature, that's classified as thermal anomalies, and that's the fire hotspot. So these detected fire pixels is compared to the surrounding background temperature, and if, again, the pixel exceeds a calculated threshold, which will vary by land surface, like deserts will have a much higher threshold compared to rainforests, that's classified as a potential fire. And then what happens sometimes, and I've seen this for VIIRS, many hotspots are actually just a hot metal surface reflecting or being very hot because of solar radiation, or a fire that's an industrial facility flaring their gas in oil refineries or such. So that can happen sometimes, and those are false positives. So you have to add a mask or do some other analysis to eliminate those false positives. And then there's confidence classification. So for each of these thermal anomalies, MODIS and VIIRS has a confidence a metadata confidence column, which is generally low, nominal, and high, or low, moderate, and high. And that determines if you generally don't want the low confidence hotspots, you always want nominal or high. High means it's above a certain threshold, so if you eliminate low and nominal, you might just get a fraction of the fire. But in my fire spread analyses and previous work that I've done, I've generally let go of low confidence and kept the nominal and high. So with that, let's go into details of each of these satellites. So NOAA GOES has a spatial resolution of 500 to 2000 meters, varies by band. The temporal resolution is 5 to 15 minutes because this is what's called a geostationary satellite. That means it's revolving around the Earth at around the same speed, so it appears stationary from the point of the Earth. And so it's monitoring the same locations throughout time, like it's stationary with relative to the Earth. So it's only looking at the Western Hemisphere, primarily these regions highlighted, so most of South America and North America. And so that means it can provide continuous monitoring of the same region. And for anywhere in this hemisphere, it can observe things very frequently, making it ideal for real-time weather forecasting, wildfire monitoring, and atmospheric studies. So what I want to do now is show you how to look at this data, actually. How do you access this data? So I have the link. The link, by the way, all these links are in the presentation. So once I send you that, you'll have access to each of these links I'm showing. But this is the place where you select regions of the world that are monitored by GOES, and then you can you can actually access some animation. So let's go to Mexico, just because I've seen fire hotspots in Mexico yesterday, and you can look at any of these animations: geocolor, air mass, dust, fire temperature, and each of the individual bands as well. Now we are interested mainly in fire temperature, so let's look at animation loops here. And it looks kind of weird, reddish and so forth, but if you zoom in, there's a color bar here that shows you how to read this map. and this is fairly real time. These animations update every 15 minutes. So this is a 4-hour loop of 24 images, and that's updated every 10 to 15 minutes. So let's see. Yeah, I can see. Do you see? This is a pixel here that's colored a little slightly redder than the background, and there's a mask that eliminates other background temperature. But let's go to, let's see if there's anything going on in California. Animation loops. This is a good check for you to understand how. I think California is not having fires at the moment, which is good. Had enough. But yeah, I just wanted to show you that you can access this live animation data and download them on this website that I'm showing you. And we'll go over how to actually download this too. Instead of just viewing them online, you can actually download fire hotspots as shapefiles and then do analysis on top of it. So yeah, that'll be very useful for you. So yeah, anyways, this is really cool. It basically animates images, and then you can see what's happening where. Here's a potential fire hotspot, an anomaly growing here. This is somewhere in Central America. So yeah, let's go back to the presentation. So yeah, GOES covers the Americas. So if you're anywhere in North or South America, you would want to use GOES, especially for emergency management or tracking wildfires for prevention purposes and in a real-time manner. Spatial resolution of the fire hotspots from GOES is 2 kilometers. And yeah, it allows near real-time tracking. It's ideal for emergency response. And so if you work with fire teams in the Americas, this is your go-to satellite. This is what you use. So I showed you how to access the animations, but let's go to the data access link for GOES. So this is part of NOAA's hazard mapping system. And let me see if I have it pulled up. Yeah. So hazard mapping system, fire and smoke product. So you can select on fire and select format. Now this is, again, coming back to my review, this is a vector format. So you want to select text, shapefile, or KML. Right now I'll go with shapefile. And just to get the dates of the LA fire, I'm going to select 7th January 2025 to let's just select 10th, right? And there are 4 files. Let's just download a few of them. And I have these pulled up. So I've downloaded this beforehand, just so you know. And I've mapped, let me see if I can pull this up, QGIS. So while that's loading, what I've done is mapped the extent and seen the difference between 7th, 8th, 9th January. So in a second, once that loads up, we'll see these GOES hotspots and compare the dates between them. This is for LA. So we're looking at Los Angeles fires, that time range. Okay, it is opening. This is a heavy software, by the way. How many of you use QGIS or have used ArcGIS, QGIS, some version of this before? All right, so let me know if you can see the QGIS opening. It is open on my end. Let me know if you can see it. All right, awesome. So basically what this is showing is the downloaded hazard mapping system GOES fire hotspots. And what I'm comparing is the green hotspots are 8th January near LA, and you can see both the Palisades fire and the Pasadena Eden fire hotspots. And then I'll switch on the red hotspots, which are from 10th January. So this these areas were burned on 8th, and then the fire expanded northward on both ends. That means the wind was moving in the northeastern direction somewhat. So this is a way to determine the fire spread, so you can do a post-fire analysis with GOES data. I will recommend something different, but yeah, this is how you can access GOES data using the hazard mapping system service. And there are APIs as well. We will get into that on another session because it's another bucket of things. We will look at VIIRS API later today. So that's one call we'll be doing. But yeah, this is an easy way to just visualize and access and then determines fire spread using the time range and a location. And I zoomed into LA. There are more hotspots elsewhere because what I downloaded is not just covering LA, but it's a nationwide data set. And you can see hotspots in Midwest. Those are likely crop fires. Florida too. So many of these isolated pixels are probably crop or prescribed burns or something small. But when you see when you see hotspots that are collected densely, like what we're seeing in LA, that's an actual wildfire. It's not a isolated thing. This is actually a wildfire. So this is how you can determine what's where. Now let's go back to the presentation. So that's how you can access GOES fire hotspots. Now let's talk about MODIS, and we'll be doing our code file analysis that I sent you all. So NASA's MODIS sensor is, again, spatial resolution is anywhere between 250 to 1,000 meters. The temporal resolution, meaning the revisit time, is 1 to 2 days, and the period of record is 2000 till now. So it has a fairly high amount of temporal coverage, 20 years plus, 25 years. My brain's in 2020. It's 2025. So yeah, 25 years plus period of record, which is quite powerful. And MODIS sensor is on 2 satellites, Terra and Aqua. It's coarser than Landsat, but it captures 36 bands. And it's a more frequent revisit time compared to Landsat, which is about 8 to 16 days, depends on the satellite. So yeah, MODIS dates back to 2000, has a 1 kilometer spatial resolution. Remember, GOES has 2 kilometers, but it's very fast. MODIS has 1 kilometer, but the temporal resolution is 1 day on average. And yeah, while MODIS offers great historical data and is useful for past analysis, its lower spatial resolution compared to something like VIIRS, which is 375 meters, can limit ability to detect smaller fires, smaller events. So MODIS, you use GOES for emergency management, immediate fire responses. MODIS you use generally for historical archival analysis and historical fire hotspot analysis. That's where it can shine because it's 1 kilometer, dates back 25 years, and has a longer coverage. So with that, let's do the exercise that I sent you. And let me know if you have this link. It should be, if you signed up, I sent it via email. So is there any, do you have the link which I sent you for the VIIRS API hotspots collab code? That's, yeah, do you have this link? Just, if not, you have it on your email, so you can open it on your time. But this is the link that'll show you how to access the VIIRS API and make calls and map the output. So what we're doing here is just importing some Python libraries, pandas, Folium, GeoPandas. There's a map key. You can use mine for now. It's a free VIIRS NASA API key. And you can get it by just registering on VIIRS API. I'll show you how to do that. And then what we'll do is this call is just showing you the options you have for accessing what data. So MODIS NRT means MODIS near real-time data. That's available from 2024 December to now, today's date. So this shows you the date range of each of these data sets to access. We'll just be using an example, so don't worry too much. And so each code within this API has its own a 3-letter code, basically. So each country has a 3-letter code. Japan is JPN, USA is USA, Peru is PER, so forth. And so what the reason I chose Japan is because there are active fires going on right now. So basically this code will call the data frame to get hotspots for Japan over the past 5 days. This number at the end denotes the number of days previously that you want to access. So if I click 4, it's previous 4. If I click 5, it's 5, and so forth. And so what I'm doing right now is running this, and it shows me the data frame of MODIS, or actually this is VIIRS. Let me click MODIS. Hold on. MODIS is here, so I'll just copy this data ID, put it in here, and run this. So these are MODIS hotspots, and it tells you the country ID, latitude, longitude. This is the brightness, temperature in Kelvin, and then it tells you the acquisition date, time. This is acquisition time, and satellite instrument confidence. Now MODIS confidence is between 0 to 100. The closer it is to 100, the more confident and likely it is that it is a fire, actual fire, not just a random hotspot that is a false positive. If it's something, so what I've done is, if it's below 40, I've discarded MODIS hotspots that have a confidence below 40, because that's generally low confidence. 40 to I think 75 or so is nominal, meaning moderate confidence. It's likely that it is a fire, and then above 75 is high confidence, that is almost for sure a fire. So you want to discard any hotspots that have a below 40 confidence number, and then it shows you FRP, which is called fire radiative power. That's another measure of how strong the fire is. So the higher the FRP, the more energy it's releasing. So fires with a low FRP means it's just a small fire, probably a small crop fire, park fire. But with a higher FRP, like this one, 345 or something, that's burning something big. It's a high energy, high intense fire. And that doesn't mean, because this number can vary even within a fire, even within a large fire, different hotspots may have different FRP values. So it doesn't necessarily mean that it's not a fire. It's just an intensity measurement. And then day or night. So this just tells you whether the measurement, the hotspot was captured during the day, D, or N, a night, N. And now what we'll do is visualize this data frame. So visualize this pandas data frame into Folium. So I'm just running this. Actually, yeah, that needs to be, the columns are slightly differently named for each data set. Satellite, date, yeah, okay, that should work. Let's see. Okay, so what this tells you is, it just shows you MODIS hotspots that are 1 kilometer across the whole country. This is the whole country of Japan with MODIS hotspots for that call specifically. So what you can experiment with this code by just simply changing the country name here, the country code here, the number of days here. So if you're living in whichever country, just look at the code, country code. That is going to be your ISO 3-digit country code. So take a look at that and then just change it for that country. Let's see, Nigeria. Let's see if it works actually. Yeah, so Nigeria is showing with 1646 rows. That's quite, I mean, it's a bigger country too. And let's see what happens here. I'm trying to map it. It might take more time because it is more hotspots, but yeah. Now it's showing me some hotspots in Nigeria. Again, these seem isolated, so I'm not confident that it's an actual fire happening. You want to look out for density of these hotspots to determine if it's actually a fire or is it just isolated hotspots that are happening over fields. And it's easy to do it with land cover data sets, so you might want to use something like European Space Agency's world cover data set, or any kind of land cover data set that you can find either global or your country. It depends on what you want to use. So yeah, in the past what I've done is also masked out crop lands, because we weren't looking at agricultural fires, we were looking more at wildfires that are not crop related. because a lot of crop hotspots, a lot of crop burnings are reported within this data set. So you don't want to mix that with actual wildfires, at least in my case, the work I was doing. So that's another way to sort of reduce isolated crop burning data set. Okay, getting back here. So yeah, that's one way to use the VIIRS API, and it's a way to get close to daily data or the most recent data using the API. Now, in contrast, we've talked about GOES for emergency, MODIS for historical analysis, VIIRS, which is my favorite. Name error. Let's see. Sorry, Max. I'm just seeing the chat here. We can fix some things later on in the Q&A. I'll have a Q&A between in about 10 minutes because it's breaking section. So just bear with me. If you get any error, let's go through that together. But yeah, the link that I sent should not have an error, but let's we can fix it later. Okay, VIIRS is it's a high resolution active fire detection. So VIIRS has the highest spatial resolution out of all of the out of MODIS and GOES and VIIRS. It has a spatial resolution of 375 meters, which is higher than the 1 kilometer resolution of MODIS. It's used in detecting and identifying active fire hotspots in near real time, and the high resolution of VIIRS enables detailed tracking of fire fronts and progression. So if I were to trust any fire hotspot datasets for tracking the actual spread accurately, I would go with VIIRS. So if you want to do a analysis of how it spread and get close to near real-time data, the reason I say near real-time is VIIRS operates on a 6-hourly time basis, but there are multiple VIIRS instruments. NOAA has one and NASA has one. So it can be up to 3 hours of a time resolution. So it is fairly near real time, not as fast as GOES, that's every 15 minutes or less, but every 3 hours you get 375 meter resolution data, which is amazing. So VIIRS data can be used for mapping burned areas with much higher accuracy and 3 to 6 hourly updates by combining the two, the NOAA and SNPP satellites. So yeah, so that's how VIIRS works. And so let's look at VIIRS data and how you can use VIIRS. So what I've sent you on your email is and again, these links should be on your email unless emails were incorrect. I sent all the registrants this email, so check your email link, and if you don't have it, don't worry, I'll send you this later, so you'll have access to this no matter what. So what we've done here is again, imported pandas instead of Folium. This time I'm using Plotly, and what we've done, so our team at LocalSolve basically downloaded VIIRS data, the VIIRS data for LA, and then now it's on a cloud bucket. So this is access, and it's publicly available, this file. So this CSV is being accessed from a Google Cloud storage bucket, and this function is basically loading that data and into a pandas data frame. And then this data frame shows us all of the fires between 7th January and 12th January 2025. So and this is just for LA. I only chose the bounding box for LA. And then what this code does is basically maps it. So okay, before I go into mapping, you have to enter a date here. So if I enter the date here, first date, let's put 7th January. Second date, let's put 10th January, 0110. And it should then generate a fire hotspots map and show you beautiful colored fire hotspots for for this area, Pasadena, the Palisades fire, and the Eden fire. And over each hotspot, you can actually, let's see, you can zoom in and zoom out using these tools, and hover over each hotspot and see when it was captured, the confidence it has. In this case, it's low, nominal, high. Low is generally below 40. There is a table that shows you what low and nominal and high mean. The number value is converted into nominal, high, and low. But yeah, these hotspots are only we filtered for nominal and high. Like I mentioned, low confidence fires are generally not trustable. Maybe in this case they are because it was an actual fire, but overall, low confidence fires are generally, a lot of them are false positives, so it's not ideal to keep them. So yeah, there we go. So yeah, and now I want to show you the app. So this is the part of the app, and I'm going to show you this in stages, so bear with me. But what this is showing is the same data that you have access to overlaid on a time slider. So instead of users selecting the date and users selecting and entering the start date, end date, what you can do is just drag the time slider to each time step. Each time step is 1 day, and it might take a second to load just because it's cutting the data frame, which is fairly large, and then redisplaying it onto this Plotly map. And there are many hotspots, as you saw, because it's two big fires. So let's see, and my internet is also slow, so that's another factor. But there we go. So this is a visualization, and again, you'll get access to this application. This is what LocalSolve, our team, has created. And again, this is overlaid on an OpenStreetMap, and you can see each metadata of each point here. And so over time, like let me go to over time, you can actually see the spread. So if you remember, 7th January there were just like a dozen hotspots, and now in just a day, this is 8th January, the fire spread this much. And now I'm on, let's see what date, yeah, I'm on Jan 11th, it'll load up. Take a mental snapshot of this, and let's see where it goes. So now, yeah, this moved northward, so this area is new, and so is this. And there's some hotspots here as well. So again, this is an interactive application that will allow you to at least see the fire progression, experiment with it, and see how the fire spread happened. All of this is using VIIRS data, not MODIS or not GOES, because VIIRS data is 375 meter. That's one of the highest resolution fire data set. So yeah, this explains, text explains what it means, how it's what each thing shows. So you'll have access to this whole app after the call, and that's the public release. Okay, going back. So I hope that helped in at least making you comfortable with accessing. And now what we're going to do, I'm just showing you quickly how to access VIIRS data. So VIIRS data is, again, you'll have this link, so don't worry about it. But this is an archival download, and this is what we used for creating this application. So we went to this archive download, and data that's older than 7 days is in this archive. So you'll have to go here for any kind of historical download, and continue, and you create a request, and basically you can create a bounding box across whatever region of interest. So you can, let's see, draw a polygon, go here, and again, I love Japan, and there's fires going on there. And you can choose any of these satellites that you're interested in, and from whatever date that you care about, and then you can download it as a CSV, JSON, or shapefile, and then request it. And in the end, after a few hours, you'll get an email from NASA VIIRS that'll confirm your request and send you a download link for the zip files. So yeah, that's how you download the archive files. And then what we did, the only intermediate step that I didn't show, is uploading that CSV onto Google Cloud Storage. That's a cloud bucket, so cloud storage, and you're accessing that cloud file, and so is the Streamlit app accessing that in this code. So this code is doing basically what you see on the Streamlit app above. So yeah, I hope, again, I want you to feel comfortable doing this. It's not hard work. It's just knowing where to access what and then how to use it. And I've provided at least a lot of the code that you need to access and play around with this kind of data. Okay, so what we learned is GOES, emergency, fastest time frame for fires. MODIS, excellent historical data, great for past analysis of burned areas. And VIIRS, excellent for near real-time data and highest resolution, so it's excellent for fire spread mapping. And when VIIRS is combined with GOES, I mean, that's a killer combination, right? You can get high resolution hotspots every 3 hours, whereas every 15 minutes get the fire pixels at 2 kilometer resolution, and you have a solution for near real-time tracking of fires. Okay. Lastly, I want to showcase NASA Worldview, which is, I've showcased this in previous sessions that I've done here on YouTube. Let's add layers. So I'm going to look at fire and thermal anomalies. That's what we're interested in. So NASA Worldview kind of combines this into a visual interface. And yeah, so let me turn on this. So you can see this is what we're seeing here is MODIS thermal anomalies. You can see some hotspots in Central Africa, India, Southeast Asia. And let's see, you can just visually slide this back and forth and see things. But yeah, the base map is most likely MODIS imagery, and it has these SWATs, so you see these gaps. It's not cloud masked, so it's not ideal, but it's great for at least exploring if there's a fire, and you want to see where should I download what. This is a great tool for you to use and then figure out what to download where, and look at things on a global scale too. The reason I don't like to use, I haven't shown Google Earth Engine for all of this, and the reason is Earth Engine has a lag in ingesting many of these data sets. For example, MODIS hotspots and VIIRS hotspots for the LA fires were not there even in the end of January. So I love Google Earth Engine and will be using that, but there is a data lag in many of these. So for real-time or near real-time ingestion, you should not use Earth Engine. So yeah, that's NASA Worldview. Again, excellent for a global view of things and adding more layers. As you can see, NASA Worldview has just about everything you can do with satellite data: dust storms, air quality, ash plumes, shipping, severe storms. Most of these are NASA or NOAA datasets. But if you're interested in, I think for air quality, drought, fires, I mean, it's quite good data, even vegetation. So let's go back here. All right, yeah, I already showed you this, but in one of the tabs, that was just one tab of Streamlit, we have the fire progression. I'll be showing you the other three very soon. It's a step-by-step reveal. Okay, with that, we'll enter the next section for burned area analysis, but let me take a 5-minute Q&A. So anything that you need me to answer or right now on the wildfire detection part, let's go through that. So yeah, feel free to ask questions. I see Max. Any idea why there's a lag? I don't know, honestly. Maybe if it's not being used much, or I'm not sure. But yeah, that's something to definitely ask about, because I tried analyzing VIIRS hotspots and MODIS hotspots with Earth Engine, but we had to use the actual firm's API, and that's it. Black slats caused by incomplete satellite coverage. No, those are SWATs. So each satellite, like MODIS, for example, has a trajectory. It revolves around the Earth. And when it does revolve, there's a gap left between trajectory 1 and 2. I wish I could show it, but essentially imagine the satellite rotating and then slightly increasing its width in rotation. So that gap left is the SWAT. Sentinel-2A, I'll be coming to that. That's next, so I'll wait for answering that. Can you talk about what nominal versus high confidence means regarding BTD? If both are typically included as actual fires after removing false positive, what's the importance of the distinction? Okay. Nominal versus high just means how sure is the algorithm in determining whether it's a fire pixel, and that scoring is on a scale from 0 to 100 generally. When they remove false positives, they generally remove hot areas that would otherwise be classified as thermal anomalies, like hotter areas on deserts or hotter landscapes like volcanoes, for example, mountaintops and so forth. But even after removing that, it's very difficult to get rid of things like crop burns, which are very tiny but not wildfires, gas flaring from oil refineries. So all of those things are really difficult to get rid of. So many wildfire analysts, if they're not specifically interested in agriculture monitoring, will mask croplands. So masking industrial areas, which are prone to thermal anomalies like the oil refineries, or even the mining sector too, and agriculture areas is something common in wildfire analysis. Sweet. Yes, Google is collaborating with FireSat, so that's pretty exciting. Maybe that's one reason. I don't know, but yeah. Again, I love Google Earth Engine, so please do not take this as something as it's just the fire data was not there when we needed it for the analysis. Okay, any other questions? I'll take one more question for now before we move forward with the burned area analysis, which is quite exciting too. Okay, is it possible to automate getting data from a source for yes, it's entirely possible. We've done it. There is so a lot of companies and organizations actually make money off of that. So a lot of it is confidential, but it's easy. And that's a session that I want to do later on. This is more about real-time analysis, but let me go back actually. Let me show you one thing that you might like. VIIRS ultra real-time API. So we have code that makes that calls let's see. Yeah, ultra real-time basically means getting the data in less than 60 seconds of satellite flyover for US and Canada for now. And VIIRS has this service through an API. So I'll send you this link. Let me see if I can do that right now. Nope. I will send you this link via email because if I enter YouTube, it might reverb. so I will send you that link. Basically, you can use this API for near real-time and ultra real-time hotspot gathering. And GOES itself, GOES has a WMS service. So you can look at and access and write code to get the, let's see, where is it? Yes. I'll send you that link. So I've not worked with GOES real-time monitoring, but I have done Modus and not Modus, but VIIRS near real-time monitoring, which is less than 3 hours you'll get the data, which is in fair real time. Like that's really good. So yeah, the answer is yes to that question. Okay, we'll move on. So next comes the burned area analysis, which is a big piece of what we did at LocalSolve with the application. So one thing I want to showcase is the National Interagency Fire Center, or NIFC, makes fire perimeter data available, and this is often drawn by hand or just outlined over the burned area. And it is generally shapefiles of active and past wildfire perimeters, which is updated depends, because it depends on when the wildfire is happening. But every few days it is updated, at least when the wildfires are going on. And you can access that perimeter data using the, okay, this link needs to be modified. But NIFC has a website that is really great, fire perimeter data, and yeah, it is an ArcGIS online map website that will allow you to download these data sets for as CSV shapefiles, and then you can select the area of interest. And this is a service only for the US right now. Canada has its own wildfire perimeter service, but you have to look into your country's government services if there are agencies that do this kind of work, or the equivalent of NIFC for whatever country you're in. So yeah, this is available. I will caution that it is a US only service. This is a national, meaning US National Interagency Fire Center. And so what we've done with our application is, I'll talk about burn severity in a moment, but we've overlaid the burn perimeters of those the fires that happened in January 2025 in LA with these fire perimeters. So what this perimeters display is the area in acres, the source, the mission name, and the extent of those fires. So I can switch off fire perimeters, and we'll talk about the burn severity and how it's done. But essentially, that's the function of fire perimeters. It shows you the extent of the fires, and the area is calculated as well. So these NIFC datasets often have incident reports, meaning information on fire name, location, containment status, and so forth. So it's quite useful, quite a good service. Okay, and someone asked Sentinel-2. Let's talk about Sentinel-2 because that's really a really important dataset, and that's what we used for burn severity mapping. So Sentinel-2 has 13 bands. That some of which we went through initially. Of course, RGB, coastal aerosol, red edge, near infrared, water vapor, red edge, and shortwave infrared, that we'll talk about. Temporal resolution is about 5 days, and period of record is 2015 to now. There are 2 satellites in orbit, so Sentinel-2A and 2B, and other Sentinel satellites like Sentinel-1, Sentinel-3, collect thermal data, synthetic aperture radar, other sorts of data. Sentinel-5P is more about air quality and so forth. So what we did with Sentinel data, and we'll go through the code in a moment, is basically analyzed, let's see, this is pre-burn. So what we did is got data for basically queried the Sentinel-2 collection, queried it between the last 2 weeks of December, so pre-fire, and this is pre-burn. So you can see that the area is quite green, has foliage, it's not burned. And then post-burn, if I switch this on, you can clearly see how the landscape changes. This is, and then let's go back a bit. Let's go to the Palisades area. Yeah, it takes a second to load. It's drawing all of this data as PNG tiles from the Google Cloud bucket, basically. Okay, so again, this is pre-burn, so this is the Palisades before the fires happened, and this is post-burn. So you can clearly see the difference visually on how, my poor laptop is burning. yeah, my laptop is on life support right now. But yes, so pre-burn and post-burn. So this is how we did this, and I want to go through the code of exactly how this happened. And again, this code was also emailed, so let me know if you can access it, but you might need a cloud project assigned to it. So let me know if you can't run it. If you can't, you have to create a cloud project here, or register a new cloud project and do that. So just letting you know that that's one reason why it may not run, but you should have the link emailed to you. So I'm going to change it to my cloud project. That is, let's see, where did it go? Okay, it's fine for now. What we've done, okay, so pre-fire start, what we had to select was the dates of pre-fire start. So the fire started on 7th January. We selected the dates of 15 December and 5th January. And the reason we're selecting more days is just because we want to composite and mosaic as many Sentinel-2 scenes as we can to cover the whole area. If we just select few days, Sentinel-2 imagery may or may not be there. But since the temporal resolution is 5 days, you know, it is highly likely that it's going to cover most of this area within that 2.5 week period. So you want to extend the pre-fire stage, make sure it's within the same season, but if you're doing burn severity analysis, at least I would say for Sentinel-2, 2 to 3 weeks is a good range to keep in mind for the mosaic. Now, after fire, we selected post-fire dates that basically... Wait. Hello, am I audible? Okay, am I audible? I'm not sure if I'm still on. Okay, thank you. I see my screen kind of lagging, but maybe that's just me. Okay, thank you for confirming. Okay, I was nervous. So it's cloud masking. And this is important for masking any clouds within the Sentinel-2 imagery. And then we're writing this code in a manner that if Sentinel-2 imagery is not available, we choose Landsat. So it is, you know, our choice initially is Sentinel-2 just because Sentinel-2 is 10-meter resolution, much higher than the 30-meter resolution of Landsat. So we're choosing that the Sentinel-2 surface reflectance harmonized data set, and then we're cutting it between two different collections, the pre-fire and post-fire. So we're now going to filter the date. Yeah. So this is a pre-fire image collection for Sentinel-2 or Landsat, whatever selected, and post-fire, that is between the start of the fire and end of the fire. And you can also start the fire or do this much after the fire ends. So like it doesn't have to be this first date. It can be 15th or whatever, but this date worked just because during 20th January and afterwards there was a lot of clouds in LA and it was raining, so you want to try to avoid clouds as much as you can. So yeah, we just basically filter the collection for pre-fire, before fire, and then post-fire, after fire, and then applied scale factors. This is just scaling factors for optical and thermal bands. That's something you scale for calibration basically, and this number varies by satellite. So you just want to look at that, how it's done, and added a function to mask clouds, to mask water bodies, and mask edges, because sometimes when you mask clouds and you're using two different resolution bands, 20 meters and 10 meters and 60 meters, so the edges sometimes may not have, you know, great pixels, so you just want to mask that. And then this is just a function that's not being used right now because this is for Landsat 8 cloud masking. We're just using Sentinel-2 right now. And yeah, all these masks are then applied. The cloud mask, the water mask, the edge mask, all of these are applied. So now we have two things being added to the map. As I was showing, we have pre-fire, and let's do the cloud mask thing. So we have pre-fire, so that's before the fire's even started, and then post-fire. And these are the actual TIFF, or in this case it is PNG tiles loading, but it's not on our Google Cloud bucket. It's from being served from Google Earth's engine, which is drawing from Google data centers. So yeah, this is how you can see pre-fire and post-fire, and it's fun to play around. You can actually see the difference visually. Now, now that we've done pre-fire and post-fire, what we're doing now is a burn ratio index. So let me go back to the slides to show you what that means. So normalized burn ratio is an index that highlights burned areas in large fire zones. It combines the use of near infrared, NIR, and shortwave infrared. And it detects differences between healthy vegetation and burned areas. So if you know this formula, basically, let me go ahead and then back. NBR, normalized burn ratio, is the difference between the near infrared, NIR, minus shortwave infrared, divided by NIR plus SWIR. So it's a ratio between 0 to 1, and it's just the difference between near infrared and shortwave infrared at the top and the sum at the bottom. And it's similar to NDVI. NDVI is very similar to this, except instead of shortwave infrared, it is red. NIR minus red over NIR plus red. So yeah, and a high NBR value, meaning if it's close to 1, that means it's healthy, it's not burned. But a low value indicates a bare ground and recently burned area. So that's how it determines burn severity. If previously healthy vegetation, like if a forest was completely burned down, the NBR would be lower, closer to 0. So that's how you know the health of the landscape, the burn severity of the landscape, using this ratio. Now, the difference between pre-fire and post-fire is the delta NBR, meaning the difference in the normalized burn ratio. So what we're doing in this code, back again, is, yeah, you got it pre and post, and now we're doing the same form. We're applying that formula, which is the normalized difference of, in this case, band 5 and band 7, band 8 and band 12, which is NIR minus SWIR 2 and NIR plus SWIR 2. So let's go back to Sentinel-2 here. So band, and this is why you need the band names and the band numbers. So band 8 is NIR, near infrared. Central wavelength is 0.842, resolution is 10 meters. Band 12 is 20 meter resolution. It's the 2.19 micron wavelength. So you're subtracting 8 minus 12 and dividing it by 8 plus 12. And that's what this normalized difference function does. It is just on the pre-fire image and the post-fire image, it's applying the NBR formula. So I hope that's very clear. It's just applying this formula on both of the collections, pre and post. So this one and this one. And now, once that's done, it is multiplying, so scaling it, multiplying it by 1,000. And then what we have is a difference normalized burn ratio in grayscale. And grayscale just means, I mean, you can visually see the burned areas very clearly here, but not categorize them just yet. And that's because it's just a layer with numbers. Like you have 485 somewhere, you have, let's see, 3.958. So in this case, the higher the scale value, the difference is more, right? Because post minus pre is high. So that means post was like the burned. And now what we're doing is categorizing it. So let's go back to the slides and show you how the categorization is done. So burn severity level, this is the classification of difference normalized burn ratio. So difference, unscaled difference in this case, because we multiplied it by 1,000 in the code. But unburned to low severity is less than 0.1. So if the difference is very minimal, right? The difference is less than 0.1, which is very low. Then it's very low severity or not burned at all because things haven't changed much. Low severity is 0.1 to 0.27. Moderate is 0.27 to 0.44. And if the difference between post-burn minus pre-burn normalized burn ratio is greater than 0.44, approaching like 0.5, that's when it's high. That's when you know it's badly burned. So we applied those categories to the code here, basically. And this is code adapted from the UN Spider website, and we modified many things, water mask, cloud mask, modified several things here. And now it's just classifying it in classes from 0 to 7. And so when I click on classified, so this is the grayscale, and this is classified. The legend here determines what color is how badly what color the burn severity is. So these purple areas are high severity, meaning badly burnt. Those are likely not ripe for restoration anytime soon. The soil might have issues there, and the landscape might need some more time to heal. Green areas, now I'll show you why this is also happening. There's very good reason for the safer areas in between the fire hotspots. You might be wondering, like, why is this gap there? They're coming to that soon. And then you can see near the north, the top of this, there are orange and red areas, which means moderate low severity, moderate high severity. And then there are these interesting fire breaks. You can see those are any guesses why this is happening? There's an easy answer. Why okay, type in the chat, why do you think these lines are not burned? What's here in this, in between these burned areas? Like, why is this the case? Any clues? Most landscapes. Okay, Serge, sorry. I'm gonna just answer this, but yeah, this interpretation applies to most forested, urban, and tree landscapes where fires would happen. So yeah, it is quite applicable to most regions. Okay, I see roads, rivers, water. Okay, let's see here, satellite view. Switch here. Is it? Yeah, there we go. And classified. Okay, let's zoom in, and yeah, those are actually trails. So they're not even exactly I mean, yeah, some of these are roads, so exactly roads and trails, but it's a fire break, right? These things will at least halt fire from one direction and not let it cross. So you're right. Those could have been rivers, but yeah, they're roads and trails. So this is how the code is working, and basically, in a nutshell, you do pre-fire, post-fire, get the normalized burn ratio for each, subtract them, and then categorize them by their quantity, and just color them. And that's all this code is doing. And then you see some statistics for each band and so forth. But that's the crux of this code. So what we've done in the burn severity map is highlighted this, and basically you can visually see what areas are burned how much. And I'll come to this. I'll just show you a sneak peek. What we've done, which is useful for like a layer beyond this, is mapped the vegetation type for the Palisades fire, because it was available for that region. So we know what type of vegetation was burned. We have that level of information for the species level, and we have polygons for each vegetation type, which is quite exciting, quite cool. Let's see. Yeah. So if we hover over each of these polygons, you can see, vegetation type. You can see what shrublands, what type of species were burned, and how severely they were burned. So I'll come to that in a second, but let's go back to this, burn severity. Okay, so yeah, I just showed you the Google Earth Engine code, and that entire analysis for getting burn severity, this was done on Earth Engine. And Earth Engine has excellent ingestion for Sentinel-2 and Landsat and such things, so big kudos on that. I think that's really important. So yeah, this code, you should have a link to this in your email again. I've emailed you the links to Google Earth Engine code, the Colab notebooks that I showed. So if you don't have it, email me at ankur@planetsapling.com to make sure you get it. But check your inbox. I'm pretty sure you should have it. Okay, next thing is what I was showing you earlier, vegetation type. So this is vegetation derived from the vegetation mapping inventory project of the Santa Monica recreational area, because this Palisades area within the Santa Monica Mountains is a national park area. So the National Park Service of the US has a geospatial data set of vegetation polygons for this area. And that was completed or started in 2010, completed in 2019. So this geodata is a result of aerial and field surveys, and then doing some machine learning to figure out which polygons belong where. But it is a unique geospatial data displaying vegetation type within this area. So what we did was we basically took the mode, or the most common value of burn severity within each of these polygons, and determined what species were burned how much. And also did some statistics, and I want to shout out Palak Agarwal for helping with this analysis. She basically, and Magdalena, who helped a lot with this application, she drove most of it. So this burn severity is displayed by vegetation type, and you can see that the big pod Cyanothus, which looks like this. It's a plant that is a shrub. Most of the land cover type within the Palisades area was shrubland, and this is what was burning the most. And it is dependent on fire, so it's not something that's necessarily invasive or something, but it is extremely drought tolerant, and it is endemic, native to California. So it is actually, a plant that depends on fire. And I think there's some interesting thing about this plant. Let's see. So it depends on fire to reproduce. This is one of the species that, it needs fire and to get back again. So that doesn't align with a lot of things that we learned, but we'll talk about invasives in a moment. So yeah, and then the last analysis that was done, and we need to create a map for this, but there's a urban tree cover data set for LA. And so our team basically analyzed the types of tree categories that were burned more, and ignore the other, because that's a set of many different species which were not enough by their own category, but were combined into other. We can see oak, pine, the jacaranda, the palm trees. I think palm trees had a higher proportion of burned areas, whereas oak wasn't burned as much, and this is generally coastal live oak for the most part. So you can see what proportions of what tree categories were burned, and this could help inform future restoration efforts, and especially trying to answer the question, what tree species are need to be planted where, because palm trees, eucalyptus trees, those trees are not ideal in such a landscape, and houses and infrastructure near such trees, especially eucalyptus, were affected badly. So when LA needs to plant trees again, do not plant eucalyptus, and avoid palm if you can, or keep it away from human habitation. So yeah, that's one piece of the analysis, and then let's move ahead. So yeah, mode is calculated, resulting plot, so you can determine and interactively see where's what. And then let's talk about the last piece of this app, which is what many of you may be interested in. So again, burn severity is the base layer, but I'm gonna just switch that off for now. This is a layer called invasive species by CalVeg, California Vegetation Mapping. So CalVeg has a data set for mapping invasive species within the LA County, and a lot of these species are actually very much flammable and fire hazards, basically. Especially what we're seeing here, Spanish broom is horrible. That's an invasive species that is it is fire fuel, basically. So in the information tab, what we'll see is the invasive species layer highlights where non-native species are highlighted. And for the most common invasive species, we have a picture that you can maximize and see closely. So this is Spanish broom, and it is highly flammable when dry, and I also mentioned that this area was extremely dry. It hadn't rained in LA for nearly 9 months, which is not very usual. And even the NDVI analysis showed that it was much drier than 2022 as a comparison, or the past few years, for example. And so when dry, it does create continuous fuel beds, and it grows pretty densely. So you can see in this map here that it forms strands, pretty thick strands. And unfortunately, we can't really see the vegetation unless it's like centimeter resolution imagery, but it forms these long strands of invasive plants. And then when I overlay burn severity here, there's Spanish broom or Maltese star thistle, some Spanish broom here, and it's overlaying parts of LA or Eden fire which were burned, and we don't know what type of vegetation was here in the highly severe zones, just because the equivalent vegetation data set that we have for Palisades is not there for the Pasadena Eden Fire region. And the core reason is this is land managed by the U.S. Forest Service, whereas the Santa Monica Park is managed by the National Park System. So there's a difference in management as well as data sets collected and so forth. But this at least highlights where invasive species are present. They were not, these are not the most updated data sets, because you can see I've added the date last updated metadata here, and it varies. Some things are a little more recent, like 2017, it's still old, 2010, so things have changed. And this data set was the last invasive species data set that we could get access to. So yeah. This is what we could get with the data that we have access to. But again, at least we know where some of these are, and a lot of these plants are flammable, and it's much better to remove them early than wait for a fire to happen and then this goes out of control. So yeah, this is the application. What we have, again, burn severity, an interactive fire map, pre-burn, post-burn imagery, fire parameters all over it, vegetation analysis, so you can see in the Palisades area, hover over, and this is not the only region. We have a smaller fire above it, and I think this is part of the Hollywood fire or somewhere close by, if I'm not mistaken. So we have a few of those as well, and then burn severity plots of vegetation types and how badly damaged they were. And if someone's working on restoration and you need the vegetation files, so the files listing as a CSV or Excel sheet, species type, burn severity, and also the tree species type and burn severity, feel free to contact me. I'll just send you those files in a folder. I haven't put it for download here just because that is an added functionality and needs more time, but if you're interested in using and enacting based on that information, that's what this is meant for. This tool is meant for restoration purposes. And yeah, invasive species, we couldn't, we can just overlay these things, but we couldn't do much because it's not a continuous polygon data set. It's just disparate polygons that are confirmed. But again, the date updated is quite, years old. And then this is just for your visualization, how the fire progressed using VIIRS data that you have code for. So with that was the whole app. You have these are more satellite data platforms and tools if you want to use and understand more and explore, but this is all meant for you. And then yeah, again, geospatial data has limitations. It's not the end-all be-all. I strongly believe that if satellite data sets like GOES, VIIRS, and MODIS is combined in tandem with sensors on the ground or cameras trained to detect fires, those could lead to much stronger responsive systems. But even better than that, instead of responding during the fires and doing post-fire analysis, if we understand these things, invasive species, dryness, fuel accumulation, we can prevent fires. This doesn't have to be the case. I think this fire could have been a bit more managed if we didn't have a fuel accumulation in areas that were dried out. So that's how to prevent it, and not have to worry about future disasters. So yeah, I think this is gonna end earlier than we and you can get 30 minutes back probably, but the floor is open for questions, or any code issues that you may have. So let's go over any questions you may have, and I'll be here for a while, so let me know. So I hope you enjoyed that. Let's go over questions and concerns and anything missing or something that you need to know. All right, and one more thing, if you want to become a part of the local solve community, which worked on this application, and we are going to create this. This is going to be open source, and all this code will be open source, and the methodologies, some of which you already have, is open source. If you want to be part of this community to work on such impactful projects and then replicate them in your country, that's the goal. I mean, with this administration in the US and what's going on in the world, we need to decentralize a lot of this knowledge and skill sets, and make things more open source. So that's the whole goal behind local solve, and empower communities to take climate action in their own hands, and empower data scientists to work on tangible outcomes. So yeah, let me know if you want to be part of that. Just email me, you'll get the link to register. And let's see. Yeah, and I will send you the link to the slides. So that will be on my Patreon. You can join for free for now. If you can donate, I really appreciate that. It's just starts at $6 a month. You get access to some exclusive code and so forth, but this helps pay for a lot of the work that goes into local solve and other infrastructure like cloud storage and so forth. So that's much appreciated. The link is, let me send you the link on the chat, but let's see. And the slides are already on there, so you can just join for free and then access the slides. And it is very easy to do that. Yeah. Any donations, any membership is really appreciated. It does help. This stuff takes a lot of effort and time to create. So any support is much appreciated. And thank you so much for the kind comments. Someone asked, how do you calculate the total burned area from NBR in GEE? So there are raster calculation methodologies on Earth Engine. Let me go back to the code. And yeah, you basically count the area and update the mask for any single class, class 1, class 2, class whatever. And you do reduce region over the whole area, and then multiply it by the pixel size in this case, which is 100 square meters. So I'll send you this code, but basically you multiply pixels site area, which Landsat is 900, but Sentinel-2 is 10 by 10, so 100. And then over that area of the class that you want, multiply the pixel size, so, and then you get the area. That's all there is. Nothing fancy. Any other questions on methodologies presented, anything that you'd like to take forward? And if there's anything here that you want to do for your country, that'll be great, like super appreciated. All right, I'll be here for 10 more minutes. So if you have any questions at all or any concerns, let me know. In the meantime, do subscribe to this channel if you haven't already. I mean, it's super easy. Just click the red subscribe button. DM me on IG if you need a PDF of curated resources. I have some courses that I've gathered that have helped me out in my journey as a geospatial data scientist. And again, if you want to be part of Local Solve, that's fantastic because you'll get hands-on experience in a lot of these projects. And then, become a Patreon member. You can join for free, again, get access to some free posts. And then if you can donate, are able to pay $6 a month, the price of a coffee cup, that's super appreciated. So I really appreciate any support. All right, I'll be here waiting for any questions. Happy to answer anything. Thank you, James, Aline, Katia, Max. I really appreciate it. Glad it was helpful, useful. Yes, Jennifer. So if you DM me on Planet Sapling, I have a PDF of courses that you can take. One of my favorite courses is by Spatial Thoughts on geospatial data using Google Earth Engine and even Python. So you can look into that. But again, if you want more courses, a list of it, I have a PDF. Just let me know. Thank you, Manuel. Really appreciate your contributions. Super appreciated. Thank you, Serge. Yeah. Any other questions? I'll be here on the call, so let me know if you have any other questions. Happy to answer anything you need. Awesome. And again, subscribe if you haven't already. That's super helpful always. and share this presentation once it's live. I mean, it is, but share this with your network and anyone who may feel benefited by this information. Yeah, feel free to ask anything else. I'll be here for 5 more minutes, so have some time. All right. Yeah, the slides are on a link. If you go to my Patreon, it's on the first post, so you can just access the slides through a link. You won't be able to download them, but you can access them as a web player. So it's, yeah. How do you deal with uncertainties in raster data? Yeah, I mean, this is generally covered in what's called the algorithm theoretical basis document. It tells you accuracy assessments within the raster that is produced. So, for example, MODIS, VIIRS, each of these FIRE datasets, and in this case, raster data, the burn severity data, has, you can perform accuracy assessments with ground validated data or burned area data. So if the burn severity is not showing where there were actual fires, that's something wrong in the code or something in the methodology. So you want to make sure that, especially in the case of fire, that whatever raster data you have, if it's showing burn severity data or if you're analyzing fire spread or whatever, make sure there is actual vector hotspots or actual fires that have been on that area. And then you can conduct an accuracy assessment or whatever kind of analysis, like number of hotspots per pixel, and determine how accurate it is. Drones and sensors for wildfire detection. I'm aware of some drones. Let's look at that together, but I can't name them yet. Let me see. Drone for fire detection. There are, I guess, companies creating cameras and possibly smoke sensors for detection of, let's see. Yeah, optical sensors capable of detecting fires from afar. So, yeah, these are kinds of drones that have been that have possibly a model that can detect fires using a camera, and it automates fire detection from a distance, and it's very, very localized. You can detect it beyond a certain radius. Like on satellites, you can see a state or a country, but here you can't, do that with drones. You can only do it on a very small scale. But it can monitor an area of 1,000 square kilometers. So there are many such kind of firefighting drones that do have abilities to detect wildfires. Skydio, wildfire detection systems, drone response. So yeah, these are some examples of drones for firefighting. All right, let's see. How did I categorize enhanced growth and low in the high and low? Okay, let's see. There we go. So, let's see here. Yeah, enhanced is 0, so let me just go back here 1 second. Thresholds is this 7. Enhanced, so enhanced regrowth, low and high. So okay, burn severity is when the ground is bare. The post-fire ground is, let me go back, zoom in. It's the positive difference. So what I mean by that is, let me see here. If the difference between the post-fire and pre-fire is beyond 0.44 or beyond that, it's high severity. But if it's negative, meaning some things have grown back, so if land was a bit barren in the pre-fire image, and post-fire it is growing up, has some shrubs or trees, that's where you see regrowth, right? Because it's the difference is positive instead of, or negative instead of positive, meaning the pre-fire had more barren land than the post-fire. And so that is, I'll send you the table, but that is basically what we're doing at the beginning. So first two are enhanced, let me see the palette table. I have the table in my documentation, so I'll add that in. but it's showing these numbers are likely the regrowth. So let me see here, classified, and yeah, some of these pixels are enhanced, so we can see the number there. Yeah, there we go. So in this case, the difference is -165. If I click on high severity, it is going to be, let's see, positive, right? So if the difference is negative, meaning post-fire minus pre-fire is a negative number, like -1000 or -251, like these numbers, that means it's a regrowth, just because that means that pre-fire, that land was slightly barren compared to post-fire. So in the post-fire, it's probably rained or probably had some growth. So there's some foliage and shrubs and small growth compared to the pre-fire stage, and that's all that means. So yeah, hopefully that's helpful. All right, any other questions or concerns? And I'll send you the table on a follow-up email, so you'll get that. Yes, those are correct. That's the threshold. I'll just add a table in mapping the names of the legend classes to those numbers. So I'll have that ready. It's a bit confusing in the code, I understand. I have the table somewhere in Slack, so I'll send it to you. And again, in that case, the higher the difference, the more positive it is, closer to 2000, the higher the severity. So it kind of goes backwards. All right. Okay. Make sure you can subscribe, like this video, please, and share it with your network. I'd really appreciate any support. I'll send you a follow-up link to the code files, which you already have, the Patreon on which the slides are located, and if you are interested in Local Solve, to join our global community focused on local climate action and producing really high impactful data projects on replicable level, just email me. And if you want a PDF of curated resources, follow me on @PlanetSapling and on Instagram, and you can just ask me for a PDF of the courses, and I'll send it to you. And again, subscribe. That helps me out a lot, more than you know, to grow this channel. So thank you so much again for joining this session. And if you have any other questions or concerns, just email me, and looking forward to being in touch. Thank you so much, and I really appreciate your support. Thank you. Bye.